The Big Bang, Our Universe's Explosive Beginning. Written by Neil deGrasse Tyson. Imagine the entire universe concentrated into a point smaller than an atom. This unimaginably dense and hot speck, brimming with energy, marked the beginning of everything, the Big Bang. Around 13.8 billion years ago, this primordial seed erupted, spewing forth space, time, and the building blocks of all matter. The early universe was a chaotic and scorching place. Temperatures were unimaginable, and matter existed only as a soup of fundamental particles. As the universe expanded and cooled, these particles began to clump together, eventually forming the first atoms. This marked a crucial stage in the universe's evolution. However, the Big Bang model, while revolutionary, left some cosmic mysteries unsolved. How could a universe born from such a chaotic event become so remarkably uniform? And why was the geometry of the universe so finely tuned to appear flat like a cosmic sheet? These puzzles hinted at something profound missing from the early chapters of our universe's story. Cosmic inflation, a faster-than-light expansion? The early universe, though cooling, was still incredibly small and hot. Then, in a fraction of a second, something extraordinary occurred. A period of exponential expansion known as cosmic inflation. Imagine a balloon suddenly inflating to an astronomical size in less than a blink of an eye. That's the essence of cosmic inflation. During this brief but dramatic period, the universe expanded at a mind-boggling rate, far exceeding the speed of light. This might seem to contradict Einstein's theory of relativity, but it doesn't. Einstein's theory restricts the speed of objects through space, not the expansion of space itself. This rapid expansion smoothed out the fabric of space-time like stretching a crumpled sheet. It also diluted any initial irregularities in the universe's energy distribution, explaining the remarkable uniformity we observe today. Cosmic inflation, a radical concept, provided elegant solutions to some of the Big Bang model's most significant challenges. The Inflaton Field, fueling the cosmic engine. What drove this incredible expansion? Scientists believe it was a hypothetical field called the Inflaton Field. Imagine a field permeating all of space, similar to the Higgs field that gives particles mass. The Inflaton Field, however, was responsible for driving the rapid expansion of the universe during inflation. Just as a ball rolling down a hill loses potential energy, the Inflaton Field transitioned from a high-energy state to a low-energy state. This transition released a tremendous amount of energy into the universe, causing it to expand at an incredible rate. Think of it as a cosmic fuel injection that propelled the universe into its inflationary epoch. The exact nature of the Inflaton Field remains a mystery, but its existence is supported by the remarkable success of the inflationary model in explaining various cosmological observations. Scientists continue to explore the properties and implications of this enigmatic field, seeking to unlock the secrets of the universe's earliest moments. Solving cosmic puzzles, the horizon and flatness problems. The concept of cosmic inflation elegantly addressed two major puzzles plaguing the standard Big Bang model: the horizon problem and the flatness problem. The horizon problem arises from the observation that distant regions of the universe, which should have never been in contact with each other, appear remarkably similar. Imagine 2 points on opposite sides of the observable universe. They are so far apart that light from one hasn't had enough time since the Big Bang to reach the other. Yet, they have nearly identical temperatures and properties. Inflation solves this problem by proposing that these regions were once in close contact before being rapidly pushed apart during the inflationary epoch. The uniformity observed today is simply a remnant of their shared history before inflation. The flatness problem concerns the universe's geometry. Observations indicate that the universe is remarkably flat. Its geometry is Euclidean, meaning parallel lines remain parallel. This requires an incredibly fine-tuned balance of energy density in the early universe. Cosmic inflation provides a natural explanation for this flatness. The rapid expansion during inflation stretched the fabric of space-time, smoothing out any initial curvature like inflating a balloon flattens its surface. Thus, inflation naturally leads to a universe that appears flat on large scales. While inflation smoothed out the universe on large scales, it also sowed the seeds for the cosmic structures we observe today: galaxies, stars, and planets. These seeds originated from quantum fluctuations, tiny variations in energy inherent to the quantum world. Imagine the Inflaton Field as a calm sea. Even in stillness, tiny ripples appear and disappear due to random quantum fluctuations. During inflation, these minuscule fluctuations were stretched to cosmic scales, creating regions with slightly higher or lower energy densities. These variations, though minuscule, acted as gravitational seeds. Over billions of years, regions with slightly higher densities attracted more matter, eventually collapsing under their own gravity to form the galaxies and galaxy clusters we observe today. Thus, the grand structure of the universe we observe today originated from the tiniest quantum whispers amplified by cosmic inflation. The end of inflation, setting the stage for a familiar universe. After its incredibly brief but dramatic expansion, inflation came to an end. The Inflaton Field reached its low-energy state, and the universe settled into a more leisurely pace of expansion governed by the familiar laws of physics. Think of it as the universe catching its breath after a sprint. As the Inflaton Field settled, it decayed, transferring its energy into a sea of particles and radiation. This marked the beginning of the hot Big Bang as we know it, with the universe filled with a dense, hot soup of fundamental particles. From this point onward, the universe's evolution followed the well-established path described by the Big Bang model. The end of inflation marked a crucial transition, setting the stage for the formation of atoms, stars, galaxies, and eventually, life itself. Without inflation, the universe would look vastly different, likely devoid of the rich structure and complexity we observe today. It was a brief but essential chapter in the universe's epic saga. Echoes of inflation evidence in the cosmic microwave background. While the inflationary epoch lasted for a minuscule fraction of a second, it left behind subtle but telltale fingerprints on the fabric of the cosmos. The most compelling evidence for inflation comes from the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. The CMB is a faint glow of light that permeates the entire universe, a relic of the era when the universe first became transparent to light. This primordial light carries valuable information about the universe's early conditions. Observations of the CMB reveal tiny temperature fluctuations, corresponding to the density variations seeded by quantum fluctuations during inflation. These fluctuations are incredibly small, just a few parts in 100,000, but they provide strong evidence for the inflationary model. The pattern and magnitude of these fluctuations match the predictions of inflation with remarkable precision. The CMB is like a baby picture of the universe, and within its faint glow, we find compelling evidence for the dramatic events that unfolded during the inflationary epoch. Beyond inflation, alternative theories and ongoing exploration. While cosmic inflation is currently the leading theory to explain the universe's earliest moments, it is not without its challenges and open questions. Scientists continue to explore alternative theories and refine our understanding of inflation itself. Some alternative theories propose modifications to the inflationary scenario, while others offer radically different explanations for the universe's early evolution. These alternative models face their own set of challenges and are subject to ongoing scrutiny and testing against observational data. The search for a complete understanding of the universe's beginnings is an ongoing journey. New telescopes and observational techniques are constantly pushing the boundaries of our knowledge, providing more precise data to test existing theories and inspire new ones. The quest to understand cosmic inflation and its implications for the universe's evolution remains a vibrant and active area of research. Inflation's legacy, a universe shaped in a fraction of a second. The inflationary epoch, though unimaginably brief, played a pivotal role in shaping the universe we observe today. In less than a billionth of a second, cosmic inflation transformed the universe from a tiny uniform speck into a vast and complex cosmos. It smoothed out the fabric of space-time, explaining the remarkable uniformity of the universe on large scales. It addressed the horizon and flatness problems, resolving some of the most significant puzzles of the Big Bang model. And perhaps most importantly, it amplified quantum fluctuations into the seeds of cosmic structure, setting the stage for the formation of galaxies, stars, planets, and ultimately, life itself. The inflationary epoch stands as a testament to the power of theoretical physics to to probe the most fundamental questions about our universe's origins. It highlights the interconnectedness of the very small, governed by quantum mechanics, and the very large, governed by general relativity. The story of cosmic inflation is a story of a universe shaped in a fraction of a second, a tale of extraordinary expansion that continues to inspire awe and wonder.